Hi, welcome to Chapter 9, Database Management. We've been talking about some cool and amazing things about how to create this new software system and all kinds of details from a structural point of view and a functional point of view. But the one thing that we haven't talked about so far is data management, or how to capture and maintain the information that's manipulated within a software system. And so that's what Chapter 9 is about. It's about data persistence and how I can manipulate data within my system, and then when I shut the software down, I can save that information out, and then when the software is restarted, all that information is read back in. Now, Chapter 9 talks about a variety of different ways that we can implement data persistence. The one way that we're going to be focusing in on is databases. And we are going to focus in on the variety of different types of databases, but we're going to focus our attention to relational databases. Now, it is an 8-step process to take our class diagrams that we created in Homework 5 and that we updated in Homework 8. There's a process that we need to go through in order to take those class diagrams and map them to a database so that we can mirror all of the classes that we have created and come up with in Chapter 5 for our homework, not only in our analysis model, but then more detail in our design model. We need to be able to map those classes to a database. And so we're going to be creating what is called a database diagram. We're not actually going to create a real-life database yet. We're going to leave that for the development team. But as the system analyst, we need to explain what this database structure is going to look like to our development team, and we'll be doing that with a database diagram. And it is an 8-step process that we're going to go through to take our class diagrams and to map them onto a database diagram. The first thing that we need to do is create a table for each of the classes that is listed on our diagram. Then we're going to choose a primary key. We're going to add representations for one-to-many associations and many-to-many associations. And then we're going to represent inheritance, also known as generalization relationships. And then we need to define referential integrity. And then we're going to evaluate our database and make improvements as necessary. And finally, we're going to choose data types for each one of the fields that we have mapped out or that we've decided upon. All right, so let's start with the very first step in the process. So let's look at a simple class diagram. Your textbook has been following a doctor's office for the last few chapters or for quite a while. And so let's take an example of a simple class diagram that describes a problem domain. We have a participant and a participant class. We're going to have a patient class, and a patient inherits from a participant. There might be potentially other participants, such as doctors and nurses and staff. A patient actually schedules an appointment, and a patient is going to be showing or experiencing symptoms. So this is just one domain class diagram. It also shows multiplicity. I can see an inheritance from patient to participant. I can see a multiplicity that a patient schedules 0 or more appointments, and an appointment can be associated with one and only one patient. So I see a one-to-many relationship between a patient and an appointment. I can also see a relationship between a patient and a symptom. Let me zoom in on this a little bit so we can see it a little bit better. That a patient experiences symptoms. And so if I look at the multiplicity on the relationship between the patient and the system, I can see that a patient can have one or many symptoms, and then a symptom can be associated with 0 or more patients. This would be considered a many-to-many relationship. A patient can have many symptoms. A symptom can be associated with many patients. There is an additional relationship that I can see here that says primary insurance carrier. That a patient can actually be associated with other patients. Say, for instance, if there is a provider of the insurance, and then let's say the parent, and then all of the children that go to see that same doctor would be carried on the parent's insurance. And so a patient can have a relationship with another patient object based upon who is the primary insurance carrier, and then all of the other children that are on that insurance. So what we're going to do is we're going to take this simple class diagram, and we're going to see if we can map this to a database diagram. Microsoft Visio has several different options, several different tools that we can use, and so I am going to create a brand new file. I'm going to go into the software templates, and we're going to look for, there's two different types of database diagrams that are offered by Microsoft Visio. One is called a crow's foot notation database, and another one is called a UML database notation. UML database notation. The only difference between these two diagrams is how it shows the multiplicity in the relationship between the tables of the database. And so that is the only difference between the two. We're going to go into crow's foot notation, crow's foot database notation. We're going to open up a new one. And we are going to put tables on the diagram for each one of the classes. So if I can go back to the original table, let's look at the classes that I can find on my original class diagram. I have a participant, a patient, an appointment, and a symptom. And so we're going to come to our new database diagram, and I'm going to drop on 4 entities. That means they are 4 tables. If you have already watched the video on database normalization, each one of the entities we would call tables. I need 4 of them because there are 4 classes on my diagram. So one of them, if I double click on it, I can give it a name. Let me zoom in so I can see it. One of them is called the participant. So I might label this one the participant table. In the participant, let me come back to that relatively quickly, each one of the attributes in the class is going to become a field on the database table. So our participant is made up of a last name, a first name, an address, a phone, a date of birth. This age is actually a derived attribute. That means that it is being calculated from the birth date. And so I just need the fields that the attributes that we're going to be using. Last name, first name, address, phone, and birth date. So I'm going to come back on my database drawing, and I am going to add an attribute name. So we'll have last name, and then the next attribute would be first name, and then we have an attribute address. And then I'm going to drag some more attributes on here. There's a couple of more that I need, so I'll drag another one that will be phone. And then I will drag another attribute into this particular entity, and we will call this one the birth date. All right, so we'll come back to the primary key in just a minute and how to set the primary key. So then I'm going to quickly add in the names of the entities for the other 4 classes, and then I'm going to add the attributes to it. All right, so I have the 4 different entities or the 4 different tables on my database diagram. I have gone in and labeled each one of them with the table name. I have included all of the attributes. We're going to ignore the primary key for right now. And then I'm going to make sure that I have deleted any unnecessary attributes that I don't need anymore. All right, so I've created each one of the tables, and I have added the attributes from the class diagram. The second step in the process is to choose or create a primary key for each table. As we well know, every single table in a database has to have a primary key. And the primary can be one, or the primary key is one or more identifying fields within the table. And the way that I set a primary key is I can select the attribute. If I right-click on it, notice that it allows me to either set it as the primary key. I can also set it as a foreign key. Or if I unclick both of them, there we go. Depending upon which one is clicked is the one that it will set. And so last name is not going to be a good primary key for this particular table because there's a very good chance that I'm going to have multiple clients, multiple patients with the exact same last name, especially if I have entire families that are coming. And so I'm going to actually create a new primary key for this table, and so I'm going to drop in a brand new attribute. Let's see if we can get it above. I'm going to drop in a brand new attribute, and this is going to be the primary key for this particular table. We'll call it perhaps the participant number or the participant ID. And so this is going to be a unique identification or a unique value for each one of the participants in the participant table. If I right-click on the field, I can set it as the primary key. I can also move, I notice how it has this separator between the primary key and all of the other fields in the table. Alright, so now I'm going to move this one down. Our patient table also has to have a primary key. My appointment table and my symptom table all has to have primary keys, some way that I can identify each and every single one of those. So date, time, and reason is not a really good primary key for an appointment table, and so I'm going to remove this one as the primary key. The symptom name, probably not going to be a very good primary key. And in my patient table, the primary key is not going to be a very good primary key either. So we are going to come in and we're going to add the primary keys for each one of those. So I'm going to add an attribute to the appointment table. You might call it appointment ID to uniquely identify each one of them. I'm going to set this one as the primary key within the table. Right click on it, set it as the primary key. And just so that it follows the same convention, I'll move that separator up there. The symptom table, I can add an attribute to the symptom table so that there is a unique identifier. I'm going to move it up above the name. I might add a symptom ID, and then I'm going to change that to be the primary key. If I want to add a separator, I can just drag a primary key separator and drop it in there. And then my patient table. Now, for the time being, I'm going to add an attribute called a patient ID. And then we're going to come back in just a minute as we talk about inheritance, and we're going to see if there's a better way that we can handle that. But for now, I'm just going to create a field called patient ID, and I'm going to make this particular attribute the primary key. If I can click on this there, let's see, there we go, set it as the primary key. So the next step that I see in the process is to take into consideration one-to-many associations. After that, we're going to consider many-to-many associations and generalizations, also known as inheritance. And so we have 3 different steps that allow us to try and represent the different types of associations between classes. So we're actually going to start with step number 5 in inheritance, and I'll show you why. I'm actually going to represent the inheritance first before I move to the one-to-many and the many-to-many associations. So let me come back into my participant table, and I know that the patient is an inheritance of the participant table. If I come back to my original class diagram, I can see that the patient is inheriting from the participant all of the attributes of the participant. Now there are several different ways that we can actually represent inheritance when we are on a database diagram. The first way that we can represent inheritance is because relational databases don't allow for inheritance as a functionality. The first way that I can represent inheritance is I can take all of the attributes of the parent and I can mirror those into the child. So under these conditions, since patient is a kind of a participant, one of the things that I could do is I could take all of the attributes, last name, first name, address, and phone, and I could add those to the patient table. So that a patient table would have, as a part of all of its fields, would have all of the attributes that it inherited from the parent. That is one of the ways that I can represent inheritance in a relational database. Now, that is going to make the searches of the database significantly faster if the patient already has all of those attributes that it would have inherited from the parent. The only problem is, what if a parent has multiple children? What about, in this instance, if I had a participant, and a participant as the parent had many children, such as a patient and a nurse and a doctor and a receptionist and an accountant, and it had a vendor who comes into our office and a pharmaceutical rep? What happens if that participant table has many, many children? If I am replicating all of those attributes in each one of the children, it is going to significantly increase the size of my database. And so I need to weigh the difference between how fast do I want the searches return, and I'll be able to search my database much faster if all of the attributes are within one of the table, and I only have to query that one table. Or am I more concerned about space? Because if I have to mirror attributes among all of the children, then it can make my database significantly larger to store. Another one of the drawbacks with doing that way is, let's say, for instance, I need to add one more attribute to the parent table, the participant table. Let's say, for instance, for some reason I decide that I want to track email address. Well, currently participant table doesn't have an email address, therefore that attribute wouldn't be mirrored in any of the children, which means that I'm going to have to go back and I'm going to have to modify all of the children to add an email address that should have been in the parent table. So it makes modifications to the parent table significantly more difficult if I then have to mirror those changes through all of the children, because there's a very good chance that I might forget who some of the children are. So option number 1, just take all of the characteristics from the parent and then just put them into each one of the individual children. Another one of the options is not all attributes are mirrored into the children. Let's say, for instance, that I have 5 or 6 children, and one of the children, and there's 6 attributes in the parent. One child only really needs 2 of the 3 of those attributes. Maybe a second child only needs 4. Maybe the third child only ever uses 2. And the 5th child only uses 5. Let's say, for instance, the last child uses all 6. Another one of the options that I have available to me is to only mirror those attributes in the child that the child ever really uses. This works well if all of the children do not use all of the parent attributes. Now, this probably wouldn't be reflected in this particular database that I am generating, because a patient needs a last name, a first name, an address, and a phone. And so if I was going to use the second option here, most likely all of the children have last name, first name, address, and phone, except maybe a pharmaceutical rep. I may not want to know what their address is, but I probably would want to know what their phone is. My doctors and nurses and accountants, all of those, I'm going to want to know these 4 pieces of information. So the second option will help speed up searches, because then I can associate critical attributes with the child. I may or may not have to reflect all of the attributes that were in the original parent. So it may not dramatically increase the size of my database as it would if I were just blindly mirroring all of the attributes. But once again, it makes it really difficult to update the parent. Because email, if I need to add email to the parent, I'm going to have to touch each and every single one of the children tables in order to make any changes to the parent. So the third option that the document talks about is only mirroring those attributes that are different from the parent. So if you'll notice here, we have the parent has a last name, a first name, an address, and a phone. And the child, who is the patient table, has a birth date, an amount, which is like a balance due, or their account balance, I should probably call it that. And then the name of their insurance carrier. If I want to only reflect those things that are different about the child in the child, I have to somehow relate a child back to the parent. And we do that through the primary key. The parent's primary key is the participant ID. The patient or the child should have the same primary key as the parent. So instead of having a patient ID as the primary key in the patient table, I'm actually going to make that the participant ID. So this is actually going to be the exact same ID, primary key as the parent. And this is what's going to tie the 2 of them together, is the primary key. So this third option for representing inheritance is actually going to take up the least amount of space, because I don't have to duplicate all of the parent attributes into the children. I can also make changes to the parent, and it is not going to impact it's not going to require me to make changes to any of the children. So it's going to save a lot of space. It's going to make updating or adding things such as an email address to the parent, make it easy to reflect that change to the children. The one drawback is that if I need, it's going to increase the time required for queries to draw information back out. Because I'm going to have to, using the primary key on the patient table or the child table, get the information, and then I will have to use that exact same primary key on the participant table to get the added additional information that it would have inherited. So while it will slow down response times, it is going to drastically save on the space, and it makes updating or adding information to the parent much easier. Those changes don't have to be reflected into the child. So database admins have to make a decision about walking a fine line between saving space and the efficiency of the queries and the speed of the return of the information when we query the table. All right, so now that we have reflected hierarchies or generalizations, inheritance, the next thing we'll do is we're going to come back to 3 and 4. We're going to find our one-to-many associations and then find our many-to-many associations. So when we find one-to-many association, we're going to add foreign keys to the one side of the relationship. So let's come back and do that. If I come back and I look at my original class diagram that we were using, we're going to see that there is a one-to-many relationship between a patient and an appointment. So a patient can have many appointments, but an appointment is only associated with one patient. I can see that in the multiplicities along the association line. One patient can have 0 to many appointments. An appointment can have one and only one a patient that it's associated with. So in order to represent that association in our database diagram, what we're going to do is we are going to put our primary key of the one side as a foreign key in the many side of the relationship. So the one-to-many relationship between the patient table and the appointment table, the primary key of the patient table is participant ID, which means that I'm going to add another attribute to the appointment table. I'm going to label that as the participant ID. And that is going to become a foreign key. If I right-click on that attribute, and I am actually selected on it, let's see if we can select it again. There we go. I'm going to set it as a foreign key. So as you well know, a foreign key is actually somebody else's primary key. So it's going to label it as a foreign key in this particular table. This is going to allow me to associate, this is a one-to-many, the way that we represent a one-to-many relationship in a database diagram. I'm going to move it up a little bit. All right, so the next thing that we want to do, or the next step in the process, is to represent many-to-many relationships. And instead of adding a foreign key into the many side, both of them are now many sides. For this, we're going to require new tables to represent that many-to-many. We cannot have a many-to-many relationship in a database diagram or in a relational database. So we're going to need to create a new table that will split out that many-to-many relationship. And so I see on my original class diagram, I can see that we have a many-to-many relationship between patients and the symptoms. Because a patient can be suffering from or can be experiencing many symptoms, and a symptom, one symptom, can be associated with many patients. If I look at the multiplicity on the association line, I can see 0 to many and 1 to many. This indicates a many-to-many relationship. And so I'm going to need another table that is going to split this many-to-many relationship between patients and symbols. And so if I come back to my database diagram, we're going to need to add another table so that I can break up that many-to-many relationship. So I'm going to come down and I'm going to add another entity. And how about if we just name this entity something like if a patient experiences symptoms, that was the relationship that we had, experiences, then I'm going to have an experience symptoms table. Oops. Because that relationship was a patient experiences symptoms. And so I need some way to be able to break that up. And the way that we then break up a many-to-many relationship is that we are going to put the primary keys of both of the many sides into the brand new table. So the patient's table primary key is participant ID. The symptoms table primary key is symptom ID. And so I'm going to add those both as primary keys in this new table. And so I'm going to put the primary key of the one side participant ID, and then we're going to make this a primary key. I'm going to put the primary key of the second table, symptom ID, and then we're going to also make this a primary key as well. And then I'll remove this bottom attribute out of there. The idea is now I have broken up the many-to-many relationship between a patient and a table, or symptom, excuse me, because a patient experiences a particular symptom. And so we can have multiple, a patient ID is experiencing a variety of different symptoms. We have a symptom that is experienced by a variety of different patients, but each one of these two combined together are going to create a unique identifier within that table. So the next association that I see on our original class table, or class diagram, is this association that a patient object has with another patient object. One of the patient objects can be or is the primary insurance carrier, and that primary insurance provider can have additional people who are carried under their same insurance. And so we need to somehow represent this association that a patient object can have with it itself. This is actually a one-to-many relationship because there is one primary provider, and there can be 0 or more people who are being carried under that particular insurance. So what we need to do is we need to represent that relationship back on our database diagram. And the way that we're going to do that is we're actually going to create a whole other table. Since a patient cannot be in association with a patient itself, we're actually going to need to create a new table. And how about if we call this the insurance carrier? The insurance, we'll call it. So we're going to create a table that is all about the insurance carrier. And so what we need to know about an insurance carrier is we need to know the name of the insurance carrier. And so I'm going to indicate that this is an attribute that is the name of the insurance carrier. And we also need a primary key. And so an insurance is carried by a particular person. So I'm going to make the primary key of this one to be the participant ID. So this primary key is going to tie back to a specific person. Participant ID, I'll be able to find out the name of the insurance. I'm going to remove this attribute here at the bottom because I don't need it. So this is going to be the name of the insurance, and this is going to be the ID number of the patient who is carrying that particular insurance. But what I need to do is, inside of the patient table, instead of calling this the insurance carrier, I actually need to know the primary. So I'm going to call this one the primary insurance carrier. Because I need to know if this particular patient is the primary insurance carrier or not. And so this is going to be some kind of a Boolean value that will allow me to say yes or no. This particular patient with that particular ID is the primary carrier or not. And then I can hit the insurance carrier table to find out what the name of that particular insurance is. And then so I have split off that particular relationship because we can have multiple patients, and we're going to see which one is the primary insurance, and then I will be able to find out the name of the insurance carrier, or the name of the insurance. So once we have mapped out each one of our individual tables, now what we need to do is we need to add associations between them so we can see which tables are connected to which. For this, instead of just using the regular association lines that we had on our class diagram, we're actually going to use a crow's foot notation for this. So, crow's foot notation is just a graphical way of representing the numbers that we have been using in the past. And so here's the notation symbols for a cardinality that is 1 to 1, one and only one. The example would be a car can have only one license plate. It has to have one, and it can only have one. This is a representation of a one and only one. So if you'll notice the crow's foot notation, the symbols it would appear that on the end of the line that there is a one and only one. So I see what appears to be two ones. As I look at it, I say one and only one. The next one is a one-to-many relationship, such as a car can carry one or more people. That would be a one-to-many relationship because one car can carry one-to-many people. That relationship is represented by, if you'll notice, what looks like the one, and then the lines that look like legs are the many. So this particular symbol is one-to-many. You may be able to guess that this is zero or more, zero-to-many. Because I see something that represents a zero, the symbols that I would interpret to mean many. So the example would be a driver can drive no cars. Let's say, for instance, I have a bus pass and they don't drive any cars at all. Or they can drive a lot of cars. So zero or more cars, that's the idea of zero to many. And then we have 0 to 1. This means a car can have no driver and it's sitting in the driveway, or a car can have one driver and one driver only if we ignore driver's ed cars. So this is the symbology, the crow's foot notation that would indicate a multiplicity or cardinality of 0 to 1. So we're going to come back to our database diagram and we're going to add this cardinality as we join each one of the tables to the tables that they are associated with, and we can indicate cardinality or multiplicity using crow's foot notation. So let's come back and let's identify the relationship that we have between the individual database on our diagram. So let's look first at the participant table and the patient table. There is a one-to-one relationship between the patient table and the participant table. For every person, or every patient, I should say, every customer in the patient table, there is one and only one record in the participant table. So this is a one-to-one relationship. So what I'm going to do is I am going to select on the relationship. I'm going to make sure that I am selected on the connector tool. Make sure that I have the connector tool selected. For the time being, I'm going to pin that to the ribbon. And then I'm going to select the relationship, and it is going to allow me to connect these two together. All right, so once I have a connection between the two, I can now choose what I want the symbols on each end to look like. So if I want to set the beginning symbol, remember this is a 1 to 1. So this is one and only one on the top side or on the beginning, and then I'm going to set the end symbol to 1 and only 1. And so now if I zoom in on it, I can see the crow's foot notation that would graphically indicate to me that this is a one-to-one relationship. A participant can have one and only one patient, and the cardinality go in the other direction. A patient can have one and only one participant. Perhaps I should say be associated with one and only one participant. All right, so now let's look at the relationship or the cardinality that we have between the patient table and the appointment table. Let me zoom out on this a little bit. So let's look at the cardinality. And a single appointment can be related to one and only one patient. So I can see a one and only one relationship there, which means that I'm going to put a relationship between these two. And remember, we read cardinality, so the cardinality is read towards the far end. So what I'm going to do is I'm going to set the end symbol of this one to one and only one. And so I should be able to zoom in on that and see an appointment is associated with one and only one patient. But a patient can have 0 or more appointments at any one given time. So I need to set the cardinality on the other side, setting the begin symbol to 1 or more. Because a patient can have 0, I said 1 or more. A patient can have, this is the begin symbol, 0 or more. There it is right there, 0 or more. Appointments. At any given time, a patient can have 0 or more appointments. So if I zoom in on that crow's foot notation, I can see the 0 symbol followed by the many symbol, which looks like the little lines or the little legs. All right, so there is a relationship between the patient table and the appointment table. We've identified the relationship between the participant and the patient tables. So now I'm pretty sure that there is a relationship between the patient and the symptoms table, but remember this many-to-many relationship had to go through, because it was a many-to-many relationship, we had to take it through another table. So I'm actually going to move this down a little bit farther, because that relationship is going to occur through, to break up that many-to-many relationship, it's going to occur through the experienced symptoms. So I'm going to add relationship between the patient table and the experienced symptoms table, and there will be a relationship from the experienced symptoms table to the symptoms table, and then we need to define what that relationship is. Alright, so if we're going from the patient to the experienced symbol, we're going to see that there is a one-to-one relationship between these two. A patient is experiencing one symptom is being experienced by one patient. I know that because, see the specific patient ID. So we are identifying one single patient and one single symbol. So both the begin are going to be one and only one, and the ending is also going to be one and only one. And I can visually see that relationship. Now if I look at the relationship between the experienced symptoms and the symptom table, we're also going to have that same one and only one. So we're going to see that there is a one-to-one relationship between the experienced symptoms and the symptoms table. But if I go back the other way, the symptoms table, there can be many symptoms that are being experienced by a participant. So there might be the potential for 0 or more. So I'm going to change this begin symbol to 0 or more. So there could be 0 or more symptoms in the experiencing symptoms table. So the last relationship that we need to look at is the relationship that exists between the patient table and the insurance carrier table. So I'm going to add an association or a relationship between the two of them, and now I need to decide what the cardinality of that relationship is. And so the relationship from the insurance carrier to the patient would be a one and only one. There can only be one patient that is associated with that particular participant ID. So I'm going to set that begin symbol as a one and only one relationship. And then going from the patient table to the insurance carrier table, it can be 0 to many, which means that a single patient can be related to 0 or many insurance carrier. So I'm going to set the end symbol to 0 or more. And then we'll be able to see the multiplicity visually using crow's foot notation. So let me zoom out on this. And now we have a reasonably simple example of a database diagram. The next step in our 8-step process is to define referential integrity constraints. Now, behaviors such as constraints, indexes, and triggers are generally represented in the SQL statements that are creating the database. And so for our purposes here, we are just going to be modeling the attributes and not the behaviors themselves. Referential integrity refers to the idea that if I have an appointment for a specific customer, let me zoom in on this so we can see it a little bit better. If I have an appointment for a specific patient, and if you'll notice participant ID is one of the keys within this table, referential integrity says that participant ID had better exist. And that means that I cannot create an appointment for a participant that does not exist. That means referential integrity. So that patient would have to be, that participant ID would have to be in the patient table. Therefore, it would also have to be in the participant table before I was ever able to make an appointment using that participant ID. So for our purposes, we're going to leave the behaviors such as constraints and setting indexes and triggers to your database class that you'll be taking. And for our purposes on our database table diagram, we're just going to leave the attributes themselves. All right, so the next step in our process is to evaluate the quality of our database diagram and to make necessary improvements. And so if I go back to my database diagram, one of the things that I'm going to notice is I just want consistency. And so I noticed that I hadn't put the word table in front of this. And then I also want to represent the visibility of each one of the attributes or each one of the fields. And we represent visibility with the symbol right in front of the name of the entity, the attribute. So if you'll notice there's a dash in front of last name, first name, address, and phone. That means that it is private to the class or private to the table. And so I'm also going to make the primary key needs to be public. And so I'm going to put a plus sign in front of the primary key. And so I'm going to do the same thing with each one of these. I'm going to add the visibility to each one of these attributes. And then I'm going to leave time, date, and reason private. We're going to make each one of the keys public. And then we have birth date, amount, and primary insurance carrier. Both of these keys should be public. And we see this primary key should also be public. And then we're going to make this primary key public as well. So this is the time when I can come back and identify or review or evaluate my schema. I'm going to evaluate the decisions that I've made when I'm building this, and I'm going to make any necessary improvements. This might be the time that I have decided that the inheritance that I have between the participant table and the patient table would be better served if instead of having the participant table, if I just replicated all of these attributes in the patient themselves. That might speed up the search on the patient table. I might have another child from the participant table called receptionist. And maybe I don't query the receptionist very much. And so I don't need that speed to be I don't need it to be very fast, those queries. And so maybe for that child, I might use a different option for inheritance. But I need my patient tables. I'm constantly querying my patient table. I need it to return much, much faster. So I might change my mind at this time and decide I'm going to use the first option that we talked about, representing inheritance, by just repeating all of the attributes of the parent into the child. We can obviously use different representations of inheritance in the same database diagram. Just depends upon if I'm more concerned about the size of the database and taking up a lot of space, or if I need certain queries to return quickly. I would expect queries on the patient table to occur frequently. Therefore, I'd expect them to be very fast. I need those queries to return very quickly. But I might not do very many queries on another child, such as a receptionist or a doctor or a nurse, so maybe I don't need those queries to return as fast. All right, so let's look at the last thing, and this is adding data types and value restrictions for each one of our fields. This is the time when I'm going to come back and I'm going to add data types to each one of my fields. I've added visibility, and so I need to add data types. You have a couple of choices of the data type that you want to add. You can either use traditional programming language of data types like ints and floats and strings and longs and doubles, or you can use much more traditional database data types such as varchars. For our purposes, we're just going to use traditional programming language data types, and so I'm going to follow each one of these attributes with the data type. I'll follow it by a colon and the data type. So last name would probably be a string. And then if you don't mind, I'm going to copy that, and then let's see, I'll paste it into address is also going to be a string. I would expect first name to be a string. I'm going to represent a phone number as a string because if it's not, if I don't need to do math on it, it might as well be a string. The date and time, there might be a data type of a date and time. The reason is definitely going to be a string. Participant ID, depending upon whether you want it to be just a number or if you want it to be an alphanumeric value, I can put a string on that. Appointment ID, I could make that as an alphanumeric string. If you have a data type within your programming language that is a date and time, otherwise I might make the time a string, or I could make this time a number or an integer. It just depends on the data type that you'd like to be. In some database models, there is a data type that is date. And I would come back and for each one of the attributes in each one of the tables, I would add the data type to it. This is an example of how we map a class diagram to a database diagram using crow's foot notation.